Good morning, everyone. Welcome to another day of probabilistic seismic hazard assessment. Hopefully all of you can hear me well. Yes, no?
Yeah, we can.
All right, excellent. Let's see, is everybody here? I guess most, so we can start slowly. Today's gonna be a slight recap of what we did, and then we're gonna be moving on into further discussions of putting things together and also extending things to what you've a little bit seen already in OpenQuake, but with a little bit of theory behind. And the main idea is to make sure you guys understand what you're doing, because you may have heard the typical GIGO principle, garbage in, garbage out. If you put garbage in OpenQuake, you will get garbage from OpenQuake. It's that simple. So let's make sure that nothing weird is happening. So I'm gonna share my screen here. Where are we? There it is. Super. Hopefully everybody can see my screen.
Yes.
So back to a quick recap, the components of the PSHA process. Remember, we've discussed the seismic source characterization, our source models, point sources, areas, and faults. We've discussed our magnetic recurrence relationship, okay, and also distances to the source model and rates. And we discussed even the, let me change my pointer here. There we go. We discussed our attenuation relationship, which could be, for example, a physics-based finite element model, or, as is the usual case, a regression-based surrogate, which is the GMP, right? So remember, I showed you the Cornell classic old 1979 GMP. Now, what is missing is the last part, where we're going to put everything together to get a seismic hazard curve, okay? And that's going to be our focus. So let's try to build this up, okay? What I've shown you so far is the GMP, more or less, and the magnitude distance distribution. So if we're talking one fault and one event, just one earthquake, you can employ the total probability theorem and say that the probability of exceeding any intensity of interest is just a double integral over all possible magnitudes, all possible distances that can happen. And it's just this one. This is the GMP part, the probability of the IM exceeding any value of interest. And this is your magnitude distance distribution. Now, big question again, we've gone a little bit into that is, well, do you split those two or do you use a joint? Well, it's not that easy to do the joint, so you would prefer that. But in reality, remember this discussion that a large earthquake will have a longer fault length. So immediately, let's say usually you use it's quite often they use the closest distance to the site. So of course, for a larger fault rupture versus a smaller fault rupture, distances will change from your site. So in reality, this is almost never correct unless you're talking about a point source. For all other cases, you should talk about the joints. Okay, and if you remember, even for a point source OpenQuake, what it does actually, it understands that there is a plane. So again, it will have some kind of a fault and some kind of a rupture of that fault. So yeah, it's a joint distribution in reality. But for now, because we're going to do some simple examples, we're just going to keep them separate because it's easy. So then next important thing is you need to include the fault rate. The fault rate, the rate of events on your fault to capture multiple events. The way you do that is you pretty much multiply everything by the rate of events. So previous one was just for one event. Now you say that, okay, I want to introduce the time dependence. And the way you do that again is the Poissonian process, if you remember. And all you do is just multiply by a rate of events. Now remember, event rates can be, what events are you interested in? Do you want to care about every single event? Remember, there are earthquakes of magnitude 0. Actually, if you want to be picky, there are actually earthquakes of magnitude -1 and -2, but these are like hiccups. You don't want to deal with hiccups, okay? Doesn't make sense. So all you do is pretty much say, okay, I'm going to care about events that make sense. And usually you pick a minimum magnitude of interest. What is this magnitude can change? Typically, people will tell you that for, let's say, modern structures, a 4.5 is the minimum you would care, because otherwise it doesn't mean anything. Nothing happens. But if you're talking about an area that is that has been non-seismic for many, many years, like Groningen in Netherlands, and now suddenly it's seismic, and all the structures around are fairly old, fairly badly constructed for us seismic people. They're just like cardboard stuff, just very thin walls, old stuff. Then you would be probably changing your M minimum. Why? Because actually a 4.5 or a 5 is something like it's a large earthquake for those structures. So you would go for an M minimum of 3 or even 2. Okay, so what M minimum is kind of depends on what your structure is. Okay, we'll be discussing that a bit later on. So now you have a rate in front, and then of course you have your integral over magnitude and distances. And again, this is just for one fold. Now let's do multiple folds. And of course, if you remember, the classic Poisson trick was you can sum up the rates, it's very easy. And that's what you do. You have multiple sources, no problem, sum them up, each one with its own rate of significant events. And of course, all of this stuff in here, see, gets an I. All of this has to get specialized by source every single time, because each source has its own Gutenberg Richter, its own distribution of magnitudes, potentially its own GMPE, because GMPs get specialized, for example, for subduction zones, for crustal earthquakes. If you're on the hanging wall or the foot wall, they change. And of course, computers do not like integrals. Actually, humans probably don't like integrals if what's inside the integral is too complicated. And when you don't like to do continuous stuff, the solution is to discretize. And you make everything super computer friendly by discretizing your M and R into bins, intervals, if you will. So this is a summation. Those two become summations as well over a number of magnitudes and a number of distances. There you go. That's pretty much it. Again, when we say magnitude equal a specific magnitude of, let's say, 5 or 6 or 7, we actually mean that it falls in a bin of certain width around that magnitude, okay? That's what we mean, because remember, for a continuous distribution, equaling any value of the continuous distribution is a probability of 0. Again, this means we've discretized into bins, and we're talking about being in a bin, not equaling a specific magnitude level. Same for distance, okay? And that's how your life becomes a lot easier. Now, in order to understand what is going on inside OpenQuake or any similar program, OpenSHA, your choice, we're gonna be showing a few simple examples. These ones come from the book of Baker, so I'll be discussing those right directly from that. It's pretty nice. I think I've had it in the literature. If you go into your literature in my courses, his primer on PSHA is there, so you can check it out. Now, the first example is the simplest one you can possibly have. One source, one magnitude, one distance. This is the site. There's a 10-kilometer distance. This is your fault. It produces only a magnitude of 6.5, make your life easy, and it produces them with a rate of 1 per 100 years, or 0.001 years to the -1, if you will. So, immediately, and I'm going back to, I should go back to this. I need to quantify those numbers. Of course, sigma, there's one source, this sigma disappears. There's one magnitude, this sigma disappears. There's one distance, yay, this sigma disappears. What you got is the rate, a GMPE. This one, well, if there's one magnitude, it's 1. This one, what has one distance, this is 1. So, well, you got the GMP and a rate. That doesn't get simpler. There it is, probability of magnitude equals 6.5 is 1, probability of the distance is 10, yeah, that's 1. And there you go. Your rate of exceeding your earthquake of interest, and I hope we all agree that a 6.5 of 10 kilometers, yeah, that's an earthquake of significant interest. That's 001, the rate that we stipulated up here. So your probability, your rate of exceeding PGA, PGA exceeding, let's say, any value of X is just the multiplication of those values. The rate times what comes out from the GMP, which is probability of PGA greater than your X given the scenario values, and those two probabilities of the scenario, which by the way are 1. So this pretty much becomes the rate, this one, and what comes out of the GMP. In essence, this scenario is so simple that it's just the rate multiplied by whatever gives you, whatever CDF, the probability of exceedance the GMP gives you. Fairly easy. To make it even easier, we're going to use the simplest GMP that we can possibly use, the Cornell et al. 1979. Again, remember that's a 40-year-old thing. If you look at GMPs today, yeah, they don't look like that. They resemble that, but they're much, much more difficult. We're talking multiple parameters, okay? I don't think I can show them in one slide or maybe 10 slides. You need a little book. Anyway, it says that the mean ln of PGA is minus 0.152 plus something magnitude minus something distance. Classic. And there's a constant standard deviation, which is 0.57. For our case, we have, remember, a 6.5 and a 10 at a 10 kilometer distance. Well, your mean ln PGA, remember the bar, mean ln PGA comes out to be minus 0.979. And if you take out the log, it means that your median, remember, again, super important, the mean of the ln becomes the median when you take out the ln. Don't forget that. Please never say this is the mean PGA because you're going to be in super huge trouble. So your median PGA is 0.3758 G. Again, just to help you out, this one is normally distributed. That's classic regression theory. If you take out the ln, it becomes log normally. So PGA is log normally distributed given MNR, log normally. The ln of PGA is normally distributed. Again. So mean here, median over here. We'll be doing this lot over time. Now, any questions? Any questions? That's important. Please be careful. We're trying to combine a lot of things here. Ask me if you got any problems. We're good, hopefully. Okay, now, what do these numbers mean? Remember, we got a median of 0.37 something. The probability of exceeding this median of 0.3758, given an event happened, okay, given an event happens, this one is 0.5, 50%. That's the definition of the median. Okay, that's the definition of the median. Now, the annual rate of exceeding this number, this value, is, well, pretty much multiplied by 0.001. That's easy. So it's 0.0005. It's 5 per thousand. 5 per thousand years. That's low, but that's typical. Okay? This is your rate. Very simple, very easy. Now, if you want to estimate the rate for any other value of interest, you need to use the log normal CDF. Oops, there's a G missing here. You need to use the log normal CDF, right? And that's fairly easy. You can say that the probability of PGA exceeding any value of X, given, of course, your scenario, is 1 minus, this is the standard normal, ln X minus ln PGA. This is your mean, and this is your standard deviation. Or if you just put your stuff back in there, that way you calculate them before, 1 minus phi of ln X minus ln of 0.3758 divided by 0.57. Let's try a couple of examples. Let's say, again, remember, back to our theory, to get the log normal, you need only to use the normal distribution, but you put ln's everywhere. That's all. Now, The probability of a PGA being greater than 1G given 6.5 and 10, given your scenario, is 1 minus phi of 1.72, which is 0.044. And to make your life easier, let's calculate this number. I like to have my Excel ready. Yeah, let's see. So, let's say the median PGA is how much? 0.3758 G. And your STD log of PGA, okay, is 0.57. These all come from the Cornell equation. You got them here. And now you're looking for what? The probability of PGA greater than, let's say, X. Oops, sorry. Your M and R, which, by the way, they're deterministic. Let's just put them 6.5, 10. Okay, let's put some X's here, and let's start with a 0, 0.1, 0.2, 0.3, 0.4, and let's just put a bunch of numbers, okay? I'll just go up to 1G, or maybe more, okay, why not? 2G, I don't know, 1.5, come on, 1.5G, that's a good. Okay, now let's set it up nicely. This equals 1 minus log, let's see, come on, Excel, give it to me, log dist, log norm, come on, log, put an equal. That's the one. Remember, it has two of them. It has this log norm dist, which is just a straight number, but it says here there is a little bit of a warning sign that it's an old one. Yeah, let's use this one. Okay. Now it says give me X. That's easy. X is this one. Super. Give me the mean. Careful here. Super careful. Whenever it says give me the mean, it always means the mean of the logs. It means the mean of the normal. So be careful here. Don't get in trouble. So you're going to say ln of this one. Super. And now it gives you, yeah, standard deviation. Again, it means the standard deviation of the logs of the equivalent normal. This one is this. Don't put an ln here, please. And then it says, okay, true is cumulative. We want the cumulative. Oh, sure. We don't want the PDF. We want the CDF. Of course, yeah, it should be 0. It's okay. Sorry, I forgot to put some dollar signs here. Yeah, it's funny that Excel works with dollars. I always had some trouble with that. Let's see. Yep. I think, okay, let me see if I didn't make a mistake, just to make sure I didn't make a mistake. 1G, yeah, there we go. 0.043, 44, yeah, it's about the same. By the way, this one is 0, is num. Yeah, it's having some trouble getting the numbers right. It's actually 0. Sorry, the probability should be 1. This one is 1. The probability that if an event happens, you exceed a 0 PGA, yeah, that should be 1. So this is roughly the number that we're interested in. I'll just make it reddish or something. About 0, 0, okay, 43, 44. And if I want to get the rate, all I have to do is multiply these numbers by the rate. So if my rate of M greater than M min, again, I don't know, I shouldn't, why am I even writing those? This is just 0, 1, there's just one rate. And eventually, if I want to have the rate of PGA, oops, greater than X, you just multiply this by this. Make this a nice constant over here and put the dollar sign. You go down and there are your numbers. So that reddish thing over here, yeah, that is the calculation. 0, 0, 0, 44. I remember that always many zeros. Whenever you're doing rates, there are always many zeros, otherwise we'll be shaking a lot. Even as we speak, earthquakes might be happening outside. No, there are lots of zeros. Earthquakes are fairly scarce, which is good. And all you have to do is, just like I did, repeat it for multiple values of PGA, and you're supposed to get this line. And by the way, here are the numbers we estimated. Yeah, I didn't have a 003758. Oh, why not I include it here? Let's make sure. Let me insert a little number here. I insert the shit row. There we go. I'm just gonna put the 50% value. Equals this. There we go. Yay, you get exactly 0.5. Obviously, the probability of exceeding the median is exactly 0.5. We should expect that. And now, if I go ahead and just create graph of these two, come on, where's your graph? Insert chart. We want one of those scatter graphs. Maybe this one. Here it is. Of course, it looks better if you put it in log, which is the typical case. Axis, let's say, come on, logarithmic scale. There you go. Yes, you have trouble with 0. We knew that before. Come on. It's always a bit of tough spot to do this right. No, I don't want multiple area. Format axis. Thank you, sir. Logarithmic value. There we go. And it should cross somewhere on the left. Come on, where are you crossing? Axis value, I don't know, 0, 0. Yeah. That should work. Anyway, needs a bit of formatting. Who cares? This one is pretty much this one. That's your first hazard curve, gentlemen, and you did it all by, okay, not exactly by hand, but by Excel. Sorry. Any questions over here? Pounds, unit, axis value, 001. Yep, your first hazard curve. Should be the same. It is the same. Any questions? You play with Excel, you can repeat all these examples very easily. No problems. Okay. Back to our main. What is quite important to know is things progress very, very quickly to very small values, okay? The larger values you're talking about, remember this one, we wanted a value that was about 3 times. From 0.375, we just went 1G, which is almost 3 times that one. And the rate dropped by, wow, 0.05 to 0, almost by 10, more than 10 times. So this one drops very rapidly. This is classic. Again, whatever I'm showing you here, it's quite classic for hazard curves. It just drops very rapidly. Now, that was a very easy, simple example. Let's go check out slightly more interesting one. Again, it's the same as before. The fault A is the same as before, but we've just added another fault, that is 20 kilometers away. But now that's a larger fault, and it can produce a magnitude of 7.5. And of course, that magnitude happens much more rarely. That's typical. The larger the earthquake, usually the more rarely it happens. So 7.5 at 20 kilometers, 0.02 events per year. This one was 0.01. This one's 0.01. This one is much, much less frequent. Now again, from the Cornell GMP, you can get a median PGA of 0.5639, again, distance of 20, magnitude of 7.5. And now it's quite easy, for example, to play around with. For example, in this case, why not go back to this value that we had before? Remember this 0.3758. Now, given 7.5 and 20, the GMP tells you that, you do your little thing with the log normal, 0.761. Whoa, that's a large number. If that 7.5 earthquake happens, you have like a 76% probability of exceeding 1G, which is a lot. Now, all you need to do is to combine what you had before. Let me go back, which was, what was the, come on, there you go, somewhere here. Come on. Yeah, you want to combine what you find for this one, which was a number of, come on, what was it? Yeah, the 0005. You want to combine it with what you got from this fault. Here's how you do it. The numbers I got from fault A are over here with the rate of fault A. I remember 1 in 100 years. So it's just 001 times 0.5. The total result is 0.05, so, or 5 in 1,000. Too many zeros, 5 in 1,000. Okay? If you add up the rate from fault B, it's now 2 in 1,000 rate times the 76% we found before. There you go. And you get a rate of pretty much 1.5 in 1,000. 5 in 1,000, 1.5 in 1,000. Total is about 6.5 in 1,000. Not so bad. 6.5 times every 1,000 years. Wow, that's rare. And again, 0.37, 0.38 G, that's not a small number. Remember, 0.38, let's say for Europe. Wow, that's like one of those most seismic regions, really seismic region. Remember the maximum, for example, for Greece is 0.36 G. That's fairly high even for Europe. Okay, that's rare, but yep, sure it is rare, but it's a pretty large PGA. Now, let's repeat this again for the PGA of 1G, or let's say the PGA of exceeding 1G in reality. We have the values for fault A. Let's do it also for fault B. It's just a straight up application again of the log normal distribution, super easy. PGA greater than 1, again, given the scenario B, 7.5 and 20 kilometers. And you just multiply again, you just take 1 minus the CDF, and you get a point about 0.60. Okay, now remember, for 0.38 or so, we had 76% probability of exceedance. Remember, they drop fast. If you go to 3 times that, it drops to 0.15, 0.16. Makes sense. It drops much faster, not linear. So again, all you need to do is simply sum up the rates. So what you got from fault A and what you got from fault B. Here you have a 001 to 0043. Anyway, you get 7 in, almost 7 in 10,000. And over here, this one gets a 4 in 10,000. This one gets a 3 in 10,000. Total 7 in 10,000. That's really, really rare. And it's meant to be. Again, it's 1G. That's like a city destroying event. It's huge. Again, it can happen 7 times in 10,000 years, which means that we probably haven't witnessed it yet. Now, if you repeat this in the same way, if you do your little Excel in exactly the same way I did it before, here's what you get. And by the way, it's fairly easy to do. Let me show you. And all I'm going to do is I'm going to take this one. I'm going to copy paste it down here. Why not? And in this case, okay, that's okay. I'm going to do, okay, no, I forgot, sorry. I need to, I should have copied it a bit to the right. Go. It's better if I do that. And copy over here. So this would be fault A. And this would be your fault A, fault B. Super easy. I just need to make sure I don't make a mistake over here. There we go. This one would be now 7.5, and this one would be 20. And of course, I need to change these numbers. The only thing that needs to be changed is the median PGA. Get it from here. What was the median PGA? Come on. Yeah, 639. Had it. Good for us. Go. And here are the new numbers. Yeah, we don't need this one. Yeah, this is a little bit out of turn. I'm just gonna remove it. Guys, delete entire row. Sorry, shift. Yeah. So, no, I should not change it. Let's put 0.375. There we go. So now all you need to do is get the sum of the two. So this one is fault A plus B. And it's actually super easy. You just say, I sum up this one. Oh, I forgot the rates. Oh my goodness. Sorry, 0.2. There you go. Now you need to sum this one plus this one. And let's go down. There it is. So all I need to do let's make a copy. All I just need to do is make this larger, and in here introduce select data, new ones. I also want add series name, I don't know, fault B, series X values, the same. Series Y values, it's this one. Okay. So add another one. I want series name should be this one. Select values for X is this one. Excellent. Select values for Y. It's just this one. I press OK. And there it is. Let me just increase it a little bit. There we go. So you got your fault. You need a legend. Yeah, come on, insert the legend. What is the legend? Need a legend. Okay. Okay, not obvious. We'll figure it out later. I don't like it. Always, every time we change Excel, something weird happens for my knowledge of things. Anyway, this will be fault B. This will be fault A. This is the sum of the two faults. Okay, I'll just go back to my presentation. Oh, all I did was copy this over here, and then I just summed everything up, okay? Nothing really crazy. And back to the presentation. There we go. Now, if you sum up the two faults, obviously you get a line that envelopes both of them. Remember, fault A is the one that is closer and has a lower magnitude, but higher rate. That's typical. Again, lower magnitudes happen more often. Okay? Now, this other fault is the B fault. It has a rate that is much lower, obviously, but a much higher characteristic magnitude. Now, the difference is important. Let's check a few things, okay? It's important to check a few things in your hazard curve, so make sure you don't screw things up. This one is the rate of the minimal event. This one, oh, come on. This one also is the rate of the minimal event. So this one we expect to be actually, it's exactly at 10 to the minus 2 because it was 001. This one, okay, it's not, oh yeah, actually 0002 is 2 in 1,000. So this is 1 in 1,000 plus 2 in 1,000. So those two, they'll give you a minimal event of 1.2 in 100 per 100, right here. This is a classic thing to check to make sure you have not done anything wrong. Make sure that if you look at the left side of your hazard curve, you get back the rate per fault. And you do. Okay, again, the 1 in 100 and the, sorry, the 1 in 100 and the 2 in 1,000. Fault A, fault B. So obviously, fault B starts much lower. Yeah. So fault B starts much lower than fault A, obviously, because they have a different base rate. Now, as they go forward to larger PGAs, higher PGAs, what you're gonna see is that fault A drops faster. Why? Of course it drops faster. It's a smaller magnitude. It's supposed to drop faster. The larger magnitude drops slower. And there is a spot, it's about, I don't know, 1.5 or so, where the second fault, the further fault, the one that's farther away, is actually going to contribute more to your hazard. You see that? So above this, about 1.5 G, it's not the close by fault, but it's the distant one that contributes more. This can happen. This is actually, it's quite often the case. Usually your frequent hazards are dominated by small nearby faults. Your larger hazard, your larger, let's say, levels of ground motion tend to be dominated by larger events at another, more distant fault. But again, this all depends on the site. For example, if you're talking about California, especially like something like Palo Alto, San Francisco, where San Andreas goes right through, yeah, okay. That's a big fault right there. It probably dominates also your short, your low level intensities, your high level intensity kind of dominates everything. Okay, that's a special case. But for a lot of sites, it's usually small and quite often unknown little faults nearby that dominate those events, and larger faults at a higher distance that dominate this area. Okay, so this is quite often the case. Now, let's go. Any questions for this? Any questions? Are we happy? If yes, I'd say we'll take a little break and then I'll continue with another example, okay? Did I lose you guys? You there? Okay, take a little break. Yes, please. Okay, super. Take a little break. See you in like 10, 15 minutes. Okay? Have a coffee. Welcome back. Hello. And let's go back to our example. This one. Again, remember we just discussed the two faults case, and again, that was an easy example. Fault A, fault B, each one just a specific magnitude, specific distance. Let's just go to something slightly more interesting. Come on, disappear. So in this case, we're just going to look at a point source with Gutenberg-Richter distributed magnitude. So again, the same. It looks like fault A. Lot 10 kilometers away. It's just a point source with a varying magnitude. I remember before that I actually had a fault. Now it's a point source. Why a point source? Well, yeah, that's a trick to avoid computing the joint distribution of magnitude distances. Okay, by keeping it as a point source, and I don't need to work with the other stuff. Just like, okay, no problem. I can separate magnitude distance. And let's say here we have 002 events per year with a magnitude of greater than 5. So we have a bounded Gutenberg-Richter relationship, and M minimum is 5. Again, that's an assumption, could be less. I have an M maximum of 8. That's pretty good. And a B, the slope of the Gutenberg-Richter law, is about 1. Again, I remind you, this is the CDF of the GR relationship, the bounded one. And of course, your magnet can rate from the minimum to maximum. So let's look at the classic, super basic example of what we can do with this one. Let's get its hazard curve, okay? So your probability, of course, of a distance of 10 kilometers, that's one, easy, makes our life simpler. Your rate of events for this specific fault is, well, 002. That's easy, we got it covered. So your PSHA basic equation becomes very simple. There's a 002 in front, which is the source rate. And then you just sum up over, well, you got to sum up now. It's not as easy as just a multiplication. Now you have to do a bit of a summing up of different magnitude scenarios. So the GMP, given the magnitude, distance is given, thank God, and then your probabilistic distribution of the magnet event. Again, this is a continuous distribution, but we've discretized into bins. Now, so this is pretty much a PMF of the Gutenberg-Richter distribution. You can derive it from the CDF by just taking, you can take, for example, let's say you want to look at 5 and 5.5. You just take the value for 5.5, you take the value for 5, you make the difference, and that's it. That's pretty much your PMF. So you discretize by using the CDF. Very easy. So here are the results. Unfortunately, you cannot do this without a bit of Excel. From the very start, you need a little bit of Excel to do it right, even for just one case. So in this case, we're just looking at PGA greater than 0.2G. Okay, where we start. Let's make it just for 0.2G. Even just for 0.2G, you need to look at all the different magnitudes. And here we've discretized with the 0.25 bin width. Starts from 5, goes to 775. Of course, again, remember it's a bin width. So this 775 means from 7.5 or less to 8. So it's a 0.25. It's a bin width. Now, this is your probability of being in this bin, of residing in this bin. This is your probability given by your GMP of exceeding 0.2G, given that the event happens at 10 kilometers. Okay, we knew that. And it has a magnitude of 5. And here is the overall discussion, the probability of your PGA exceeding 0.2G, given your magnitudes, and that it occurs. If you sum all those up, you get 0.269. Let's see what this means. It means that your probability of the PGA exceeding 0.2G, given all those things, is 0.2. Sorry, it's 0.269. If you want to get a rate, you have to multiply by the rate, which is 0.002. So you get, let's say, 5.4 in 1,000. 5.4 events in 1,000. That's not so bad. Again, it's important. Don't look at this one. This is how often the event happens. This is how often, given the event happens, you exceed the number. Obviously, the larger events, they're much easier to exceed this 0.2G. The smaller events are less easy to exceed 0.2G. Okay, this is 0.12 if you have like a magnet 5. But if you go to a magnet 7.75, it's like, yeah, guaranteed that we'll exceed it. But you need to multiply the two to get the contribution. Again, remember, this is two different things. This is how often the earthquake happens and how often the given earthquake exceeds. So small earthquakes are frequent, but they're weak. Large earthquakes are infrequent, but they're very strong. Multiply the two, and this is the number you should be looking at. Now, look at this number and you see actually the contribution. You can see very easily that the contribution of the smaller events is the most important one. See, this 0.269, about half is coming up from magnitudes 5s and 5s to 5.25s. About half of it. You add up a couple more to get to about 6, and you pretty much have it all. Okay, so event is right here. Actually, it's right this one, but okay, let's put it this way. Both of them are really important. Now, do you see anything wrong in this? And honestly, I am going to stop and I'm going to wait half an hour until somebody tells me, yeah, I see something wrong or not. Do you see anything wrong with these numbers? And I'm not asking about the numbers themselves. I'm just asking about their magnitude relative to the other ones. Of course, the sum up is 0.269. That's fine. That's no problem. There's no mathematical error happening in here if that kind of helps you. In terms of practicality, you see any problem with those numbers appearing at the start of this discretization? Any takers? Would you feel more comfortable if they happened at the end? Let's start stupid discussions. Would you feel more comfortable if these two numbers, the most contributing events, were over here? Or how about if they appear in the middle? Come on. Oh, I'm going to get a list of participants here. I'm going to start asking people.
Maybe we
Crystal,
take
tell me.
smaller magnitudes.
Maybe we should have smaller magnitudes. Is that what you said?
Yes.
Why?
Because I see that the magnitudes of 5 and 525 have a large contribution. So maybe there are smaller magnitudes that also have a large contribution.
That's the problem. Maybe we're missing something. Remember, your PSH, the hazard curve on the left is bounded by your smaller lambda minimum. If you go back over here, you pretty much bounded your Guderman-Richter distribution at magnitude 5s, and you just said, okay, that's the rate of 2 per 100 years. Maybe that is too high. Maybe I need to go lower. Yeah, that's a good point. Maybe we're missing some important contributions from lower events. We are. Let's go to a higher. Okay, let's go to a higher acceleration. This is the same, but now we're focusing on 1G. Okay, remember this binning, it doesn't change. It's the same number of bins and the same probability of currents. Okay, per bin, it doesn't. It's exactly the same. The only thing that changes is this one. This one changes. Okay, obviously because now it doesn't say 0.2G here. It says 1G. And now you see the difference. Small magnitudes, well, yeah, the 5 has practically no chance of exceeding 1G. 525, yeah, okay. Obviously, the larger events, the 775, gets to be the most important. Then again, if you really want importance in terms of the overall sum, you need to multiply this one with this one. And this one is a very infrequent event. This one is a very frequent one. So, of course, 0 times something, 0. This one is really small, almost 0. 1 in 1,000, sorry, 1 in 10,000, apologies. 2, 3, 4, 7, 7, 7, 6, and 4. You multiply those, so you sum those together, and you get that your probability of exceeding a PGA of 1G is just 4.8 in 1,000. That's very low, but still doable. Your rate, you have to multiply by 0.002, and then you go to, 9.6 10 to the minus 5. That's a small number, but we expect that 1G is, again, it's a city changing. If PGA of 1G happens in any city in Europe, even something as seismically active and well constructed as, Athens, you will see some major changes in the landscape, okay? Major changes. It's not going to be the same city after that. PGA 1G is really a destructive event. And okay, thank God it's going to happen, let's say maybe once every 10,000 years with this discussion, with this model. And minimum is okay. Look at this. The small events matter not. So I'd say we could even go higher, but you don't want to do that. Okay? okay, for 1G, you could use a higher magnitude, minimum magnitude, but of course you want other PGA values, so let's not do that. So my minimum is fine for this contribution, for this level of PGA. And there we go. Again, your most contributing events are not on the upper end. If they were on the upper end, we might be thinking of, let's say, at least better discretizing. By the way, remember, the upper end was an 8. You cannot go higher than an 8 because that's the maximum magnitude that your source can support. You cannot go like, yeah, let's go to 9. No. There's a reason you bound on the higher. The upper end is bounded for a specific reason that has to do with physics. So if this one was a large number, most contributing or something, you wouldn't say, I want to increase the magnitude 8. Nope, that comes from a seismologist. There's a reason for that. But you may want to increase your discretization in that area, okay? Discretize a bit better. Because that 7775, yeah, just put a little bit more finer discretization there. Otherwise, don't touch it. And your most contributing events are about somewhere here in the middle. Again, not the very low, not the very high, somewhere in the middle. Okay, we're good. I like that. That is something that I can work with. That's something that makes sense. Okay? Any questions? Again, I hope you understand that it's not straightforward as, okay, let's punch the numbers, press the button, OpenQuake gives the answer. It's never like that. It's like every model, like every structural model. You look at it and you try to see if there are any discrepancies. You try to do logical tests. You try to make sure that nothing is weird. And it's not just one number. It's not just one run. You make multiple ones. You play a little bit with your discretization. You play a little bit with the little things, okay, just to make sure nothing is wrong. Nothing is weird. Again, treat it as something that is not perfect, but it needs a bit of help to be perfect. Okay, and then you won't be disappointed. So, for example, 3. And here are the results. Well, that's a nice hazard curve. What you see here. Here is the value we estimated for 0.2G. Here's the value we estimated for 1G. You do repeat this for multiple ones, you get this really nice hazard curve. Beautiful. Now, if we also wanted to do a real example, we'd have like multiple faults, more rates, more distances, joint MR distributions, but it's gonna get really weird. This is why beyond this level, you cannot do this with tables and Excel like we did. You have to do it with a computer. Okay? You have to do it with Now, this is the basics and it works very well. What we need to discuss a little bit now is the extensions. And extensions, the most important extension that we need to build upon what we've done so far is disaggregation. We've already discussed it a little bit, and we discussed pretty much finding the most contributing events in every scenario, in every case. And that's a very useful thing. Why? Because, again, talking to people about probability gets weird very quickly. People stop understanding after a while, they fall asleep. Not everybody is probabilistically trained. You start talking to mayors, you start talking to even professional engineers. Probability is not that everyday thing. Hopefully, we're going to be changing that over the years, but it's going to take a couple of decades more to get people comfortable with this. And even for us, I mean, for us researchers, even if you're comfortable with probability, it's much easier to visualize it with a few numbers that, you know, get imprinted in your brain. So it's important to recover useful scenarios for multiple reasons. They provide insight, they help you communicate results, and also they help you understand if you made a mistake, okay? They help you verify discretization, verify calculations, etc. It's very, very useful. And it also gives people some understanding to say like, okay, is that possible really? I mean, should I design for that? Should I take account for that? All of those little things. Super important. Now, formally it's called disaggregation or deaggregation. Which of the two terms to use? I think there have been papers about this, but anyway, it doesn't really matter. I think most people call it disaggregation nowadays. The way it works is just the Bayes rule. And all you need to do is say my probability of a certain event, a certain scenario. Here the scenario was in terms of magnitude because distance was all fixed up. But I can have a specific a distance as well, or a specific level of epsilon exceeding the mean PGA, for example, is pretty much, this is the rate of the of IM exceeding X given, and and you having a given magnitude divided by the rate of exceeding your IM. So again, it's the base rule. This one condition on that is pretty much both happening divided by just one happening, the condition. So all you need to do is calculate the numerator, and in reality, your numerator is hidden in the results we estimated earlier. So all you need is the rate of exceeding a certain level of intensity, given your magnitude or magnitude distance, for example. And again, it's just an application of the total probability theorem, which is actually much simpler because you have a fixed event, it's given magnitude, given R, or given epsilon, if we go that far. It's just a it's like a sub byproduct that you already incorporated earlier. So let me show you a couple of examples that will be made much simpler. Let's go back to our example 2. Remember that was fault A and B, the one we did in Excel. It had two sources, two magnitudes, two distances. And let's ask the very simple question, what is the most contributing event for a PGA of, remember this one was the median value for fault A, of 0.3758 G, all right? Again, everything is already pre-calculated. You don't need to do much work. You just need to go back to those tables and pick up the numbers. We've calculated that to exceed this number of this value of PGA 0.36 for a 6.5, that was about 0.005. To exceed it for a 7.5, that was about 0.0152. Remember, you sum up the two, you ended up with this number. Again, it was a super easy example. That was one result, that was another result, that was the third, the sum of the two. It wasn't much, it wasn't any difficult to do. If I go back to my Excel here, all I'm looking at this example 2, I'm looking at these numbers. And specifically, I'm looking at this. I should make it this one. And this. These are the three numbers I'm interested in. 1, 2, 3. See, I calculate them already. Again, this is the PGA I was interested in. The rate for the first fault, the rate for the second, and the sum of the two. Super easy. I'm just saying. Yeah. So again, 0.05, 0.0152, and their sum. Now, let's go back to this. The base rule, all that it says is pretty much, it says normalize this and this by that. That's all it does. Okay, so if you want the probability of a magnitude 6.5 happening, given that your PGA is larger than 0.36 G, it's pretty much this one divided by the total, 0.77. If you want the same for fault B, is a 7.5 here, remember, and you just go here, you take this one and you divide by this one, 0.23, and there is no, let's say, hopefully no surprise that the two add up to 1. So all you've done is you renormalized everything. You took a specific scenario, the scenario of exceeding 0.36 G, and then you renormalized all the contributing events to that by its rate. So what this tells us is that, yep, remember we've already noticed that. I'll go back in a bit. It tells you that the 6.5 is 77% more likely, 77% likely to actually produce this. The 7.5 is only 23. So that's the relative contribution of the two. By the way, if I want to go back, it was about here, 0.3 something, yeah, 1, 2, 3. Oh, by the way, sorry, it was exactly here. So you see, it's just this one divided by that, and this one divided by that. So yeah, it's obvious this one is about 3 times more likely than this one. That's all it says. Again, it's log normal, so it's distorting a bit the scale, but you're comparing this point to that point, and you're saying, yeah, this one is 3 times more likely than that to produce the 0.36 G, 37 G. That's all. And that elaborate trick over here, it's called disaggregation. And it's very easy to do if you have two events and two faults and two magnitudes, but it's a bit more, you need a little bit more care to do it properly if you're talking about multiple events and multiple magnitudes, etc., etc. So let's look at an example like this. What is the most contributing event for a PGA of 1G? Let's redo this Hall calculation again. Again, super easy. You go back to our Excel and you pick up those two numbers, 0043, 00316. The sum of those is 0074. And then again, you divide this one by that one. Oh, come on. Pointer. There you go. That's a proper pointer. You divide this one by the sum, you divide this one by the sum, and here are the results. For a 1G, now the M6.5, the fault A, is 58% likely to get the job done. The 7.5 is only 0.42. If you remember, again, our discussion on the Excel spreadsheet, that was, it's about here. Yeah, actually, it's exactly here, 1G. And remember, we're saying that at about 1.5G, 1.3, yeah, at about 1.4G is where the rates change. And now fold B becomes the most contributing. We already established that. We could already see this, right? We were looking at about here. Yeah, we're looking at those numbers. Yeah, this is 1 in 1,000. This is 1.1 in 1,000. So yeah, fold B is just becoming more important for the total. Again, all that disaggregation does is formalize those numbers. That's all it does. Okay, just formalize them and renormalize to make sure that they sum up to 1 and they give you the relative contribution of each fault, of each scenario, of each event, whatever you wish. Again, what it all does is go back. Remember, think of it as total probability theorem is about aggregating a lot of events to find out the probability that you're interested in or the rates. Disaggregation is going back into that sum, picking up those events that you're interested in, bringing them together and saying, aha, these are the ones that are most important. Okay? So, what it says is, if you want to go back to your client, or you wanted to just speak to the crowd, people, to your audience, speak on TV, I don't know, and you wanted to say, okay, here's an event I would be interested in using, it would be tough saying which of the two to use. In this case, you would say, yeah, I probably need to also consider fault A and fault B, the 6.5 and 7.5, because they're roughly 50-50. You go a bit back. Where was that? Yeah, over here. Yeah. This one, you would clearly say, yeah, I need to look at the closer fault A. I don't need to look at fault B. I wanted to characterize this event, the 0.37 to 38. Yeah, I will just look at 6. Okay. So that is the easiest way to do those things. And it gets more interesting if we go to example 3. Now, here's the fun part. Let us now disaggregate. Remember, I'm going back to our one source and multiple magnitudes, again on the single source with Gutenberg Richter. Let us now disaggregate the events for PGA of 0.2G. That's an example we did earlier. Remember, your rate of PGA exceeding 0.2G is 0.0754. By the way, I should stop here, because I believe somebody sent me a note. Did I make a mistake? Yeah, missed it. It's okay. Any questions so far on what we did? I should ask questions first. Any questions? Is everything clear, hopefully? Feel free if it's not, you're tired. Makes sense. Okay. Let's move to our multiple Gutenberg Richter distributed magnitudes. Again, we're looking at the PGA of 0.2G. Again, remember our rate as estimated was 0.054. And again, by virtue of having one source and one distance, actually fairly easy to say that the joint distribution of IM greater than X and a given magnitude is just the minimum rate times what the GMP gives you times just the probability of being in any bin. All the terms to compute this are actually already available. For example, the minimum rate is 002 that was given, and the rest come from the PSHA tabulated results. Let me give you an idea. This one is the exact same table I used earlier, the exact same table. And guess how it looks? Oops, let me get. The probability of a magnitude 5 is 0.4381. And I'm going to put everything here, right? I want to find the probability of a magnitude 5 given the PGA greater than 0.2. The probability of a 5 is 0.4381, and I just pick it up from here. The minimum rate is a 002. I just got it from the basic scenario data. Then the probability of a PGA greater than 0.2G given a magnitude of 5 is 0.1242. That should be, oh, come on, that's right here. Sorry, my animation is a bit messed up. That's right here. And my rate of PGA greater than 0.2, that's 0054. I got it from that spot multiplying by 002 pretty much, if I remember well. Yeah. So this one goes here. This one goes here, this one goes here, this one goes there, this one goes under here. You do this little thing, the base rule, and you get 0.2. So, pretty much, your magnitude 5 contributes to a PGA of greater than 0.2G by 20%. Again, remember this discrepancy. You expect to find a 20% here, maybe a 19% here, and then it's going to drop slowly. 18, 15, 10, and the rest are not going to matter that much. So again, we just formalized. It's like we took these numbers and we divided them by this number. That's all we did in reality, okay? Because the rate was the same for everything. So that's all we did. We took these numbers and we normalized them by this to see the relative contribution. And the end result, you could find which magnitude contributed the most. That's all. We already did that beforehand. So we could see it, but now it's more, let's say, normalized to 1. So, and this is exactly what the aggregation is about. Okay? Now, I'll give you a 10-15 minute break, all right? I'll come back and talk a little bit more. And the plan is for the rest of the day to just discuss the project. I see some questions came up over email. I need to remind you over here that, let me bring this up. Sorry, guys. Come on, there you go. According to our schedule, we are over here. And we're going to have a bit of classical PSHA 2 and some extra stuff, a bit of practice session, and also we're going to be discussing your project. But let's say in about 15 days from today, about here, I expect you to give a presentation of what your project is at. Again, this is not something that gets graded, but I expect you to have done something. Otherwise, you're going to reach the end and have done nothing, and we're going to be in trouble. Okay? So, take a quick break, like 10 minutes. We come back and we start discussing the PEN project. Okay? Any questions otherwise? Any questions on this aggregation? Happy? All right, quick break. Hello again. Hey guys. We're back. Had a bit of water. Voice is better. Okay, let's share our screen. There you go. I'm sorry, Michalis, thanks for the check. I indeed had missed a 0 over here somewhere. I fixed it now. So remember, this is where we were stuck last time. all those calculations. And I forgot to tell you that we can easily, there you go, so as a pointer, we can repeat this for all magnitudes very easily. I just did it for one over here, the previous version. Here, I just did it for one case. I just did it for this 5, so that's actually this number that we got. I got a 0.20, yeah, it's 0.2022. Okay. So you can repeat it for all of those, and you can get your nice little distributions, and you can even plot them. There you go. You can plot those numbers. You can see how they drop off really, really quickly. And again, this is for the 0.2G, and you can repeat that also for the for the 1G. And remember what we found earlier, that actually now the most contributing numbers are about 7, 7.25. So now, obviously, for the larger acceleration, the distribution has shifted quite significantly. Guys, everybody there? You listening to me? Sorry, it's tough. Sometimes you like speaking the wall. You're good. You're following. There you go. Thanks.
Yes.
Thank
you, yes, we're following.
All right. So disaggregated distributions, 0.2G, 1G. Now, some fun things. I mean, once you start having your numbers, you can start playing with them. For example, what is the bin width effect? Why did we choose to go with 0.25 and not something different? Okay, let's go to 0.5. Why not? This is the case, the same exact calculations, but now at the 0.5 step size. What you see, for example, as a change is just look at this number. This was previously 0.20, more or less. Now it's 0.37, roughly. Of course, it's a wider bin size, okay? That didn't really change. This one corresponds to a wider bin size, okay? Just remember that. And of course, if you look at the shapes, you see it's just a coarser, a lower resolution view of what we had before. Now, which one is better, this one or that one? Well, this one is faster to get. It costs exactly half the calculations. It's very easy to get. And also, it's also easier to identify. I mean, do you really want 525, like a 5.5 or a 6 or 6.5? It's a smaller, easier number to play with, okay? In reality, we do our binning in a much finer way. We don't do 0.25, go like 0.1, 0.005. But when you disaggregate, you often prefer to have like larger bin widths, just to be able to, you know, talk about scenarios in a simpler way, like scenario of 7.15, yeah, or 7.11. Yeah, it's easier to just say 7 or 7.5. Okay? It's just something to give you an anchor point to talk about. So quite often, funny enough, even though we do fine discretization to actually do our calculations, it's easier if you have smaller bin widths. Sorry, larger. Again, remember that's a typical thing whenever you have sample points and you're trying to put them in a histogram. It's quite often the case that choosing wider bins helps you visualize the histogram better. Okay, you'll see this also in your examples. And of course, if we're going to be talking about a real case, a realistic case, disaggregation gets more interesting. Before we had just magnitude disaggregation because distance and everything else was just pretty much fixed. Now, here's what you look at. You're looking at an actual case, actually a USGS site. You can go to their website and you can actually download these kinds of graphs very easily. If you go to USGS, and this is for Palo Alto, California. That's pretty much what Stanford is. And you got here your closest distance to the fault rupture. Here you got your magnitudes. You have your contribution to hazard. And by the way, they have also included an extra disaggregation. And this disaggregation you do by coloring the bars for epsilon. Again, epsilon, remember, is the number of standard deviations you are away from your median. So an epsilon of 0 means you're right at the median. So if you see something like it's yellow or orange, at the median, nah. Again, this is 0.63 G at 1 second. That's a very, very large value of acceleration. Again, 1 second acceleration, 0.63, whoa, that's large. And to get to that, you need rare ground motions. Rare ground motions are the ones for a given rate, right? There are ones that have a high epsilon. There are weird ones. So blue ones are really rare. Green ones are less. This is an epsilon of 2 plus, 1 plus, 0.5 and 1. So you got your greens over here, you got your light blues over here, cyan, and you got your darker blues over here. And what this tells you is that, okay, we're expecting, whoa, that's close to San Andreas. Yes, about a 7.7, 7.6. That's your most contributing one at a distance of about 10 kilometers. Remember, 10 kilometers, the distance from San Andreas, more or less. 10 kilometers away, about a 7.7. But it has to be a little bit of a slightly rare event. But it can happen. It will happen. If you want a less weird one in terms of the GMP, you have to go up to an 8 at the same distance. So this is San Andreas pretty much, contributing everything to you. This is a more distant fault or distant event, and an even more distant one. But yeah, minor contributions. The big thing for, let's say, the entire Stanford campus to watch for is this event happening right here. Right here. San Andreas, something between 7 and 8. And that's going to give you a lot of trouble. Okay? And of course, you want to disaggregate at different spectral acceleration levels. It's fun. It's a fun game. It's a fun game. Looking at all those results, having fun, checking out what's useful, what's not, gaining intuition in your problem. It's a beautiful thing. Of course, not when you have to pay for all this stuff in terms of damages, but you get the point. Right? So that's your realistic disaggregation. And by the way, you will be able to get, I mean, if you've done it already, you have done an example with disaggregation, how to get this data. Okay? Usually, if somebody wanted you to ask you to estimate something useful about this one, this is the mean return, not time, I'll say mean return period, 2,400 years, more or less. It's the 2% in 50 years. This is how this SA1 sacred greater than 0.63 G. So this is a very rare scenario, 2% in 50 years. And your mean event is about 10.3, 7.65, and 125 is your epsilon. So this is the event that you're going to be looking at. Okay? If you had two bars of about similar height, you say there's no real mean. Remember the thing, you cannot take the mean of a man and a woman. It's weird. You cannot take the mean of a family with 2 kids and a family with 3 kids, because it will tell you it's a family of 2.5 kids, which doesn't make sense. Quite often you have to be careful about this. You might see a bar over here and a bar over there. On the other side, and you might say the mean distance is 10 and 30 or 40, and that doesn't mean anything because there's no fault in that distance, okay? Be careful with means. Means can be dangerous if you don't understand them well. Okay, you can take the mean of 2 different things and get weird things. So, this needs some interpretation, but you can do it. You'll learn your results and your examples and your exercise for the term project. That will help you a lot. Now, let's turn to another interesting little thing. What about your M minimum bounds? Remember this discussion we had before that our 5 was a little bit maybe too much? How about we make it larger or we make it smaller? Well, it's important to choose wisely because you have to balance long calculations. The smaller the magnitude you get, the more bins you have to include, so the longer it takes. And of course, if you don't do it right, you got errors. And here's what it looks like. Your hazard curve is very sensitive on the left end. It's very sensitive to what minimum magnitude you choose. Okay? Because obviously, again, remember, the rate of this M min is actually what's going to appear at this spot. This rate is higher because it's a smaller magnitude. This rate is about in the middle. Remember the 2%, 2 events in 100 years it was? Okay, no, it was sorry, it was, yeah, about 2 events, yep. And this one, the 5.5 is much lower. If I had a 6, a 7, see, it would similarly change its distribution on its left side. Now, this influence affects also all small intensities. It affects 0.2G, even 0.3G. See, it's clear for me that I should go to 4.5. Based on what I see here, I should go to 4.5 if I'm interested up to 0.2G. Yeah, if I'm interested in even lower ones, if I have, let's say, old masonry structures that are in trouble and could get damaged for maybe so from 0.1G, I should probably go from a 4 or even a 3.5, okay, to make sure I don't have any problems. The way to choose that, the way to play with that is just, should we do it? Go on your analysis, start with a 4 or 4.5, and then start decreasing. Does it change? Do I see any difference? Yes, no. That's it. It's very simple. It's, again, you don't do just one analysis. You play a little bit. You vary parameters to make sure what you're getting is not sensitive to your choices. Okay? So that's important. Of course, if you're interested in, let's say, anything higher than 0.5G, who cares? It's completely insensitive. Those small events lower than 5, you don't care about them. See? They don't make a difference. So you got to do a bit of balance. Again, similarly, you need to bound R and epsilon. R is the distance, so you just cut off everything that's beyond a certain distance. And epsilon, yeah, of course, there's a plus minus 3 that pretty much everybody uses. Otherwise, you get like really weird rare events or really weird on the other side, which that's not very useful. Now, how about distance? Distance, how do you put an upper limit with distance? Okay, you start from 0, okay, and then you go maybe to 100 kilometers, go to 200. Well, it depends. I've talked to you, remember that was the first class we ever did, the first lecture, the Mexico 1985 earthquake, which collapsed several buildings in Mexico City. That happened 380 kilometers away. Oops. You should have included earthquakes beyond that. If you didn't, you missed several issues. You missed an entire destructive earthquake for downtown Mexico City. Okay, that may be an extreme case, but in general, whenever you have subduction zone earthquakes, like Japan, remember the Tohoku earthquake? Actually, wow, what was it, a couple of days ago? That was the Tohoku earthquake 10-year anniversary. That was a far, far event. You should have included that. Okay. Same thing happens, for example, for Crete, because there's a subduction zone to the south. You should include that subduction zone because that thing extends and goes underneath the island. You should include that in your analysis, okay? So, sure, you put bounds on R, but carefully understand the seismotectonic environment. Yes?
When it comes to putting bounds at the moment magnitude, I mean, I guess we start from 5 and we start going downwards, and when the curve saturates, this is good enough. When we are to put bounds on distance, do we observe the same convergence? I mean, if up until 200 kilometers there's nothing bad, but at 350 kilometers there is a huge fault, you might think at 200 kilometers and then realize that you missed something.
That's true, yes. That's why you have to be a little bit, you have to understand a little bit of your side. But in most cases, honestly, yeah, about 200 kilometers is fine. You stop seeing anything weird after that. Again, I did talk about very specific cases like the Mexico City, which was a very unique case in the world. And then even about Tohoku and Fukushima, those little weird events, those were tsunamis, mostly. It was not actual shaking that did the damage. And tsunamis, they tend to travel 1,000 kilometers if they have to. So yeah, okay, we don't do tsunami, but it's the same idea. In those cases, you should look even wider, okay? But yeah.
Thanks.
It's not a perfect problem. The more you understand your problem, as always, the better choices you make.
Thanks.
But let's say 200 kilometers is a very typical number you can use pretty much everywhere in Europe and get fairly good results, let's say. I think, do I have anything more? I think no, that's it. Okay. So that is as far as theory will go for now. And anything about to hazard PSHA. Let's, oh, sorry, where did I go? Stop sharing. Let's go to your little nice semester project. Yay, what is a semester project? Semester project. Come back to me. There you go. Let me share that screen. Apologies. Share screen. Yes. Let's maximize that. All right. Now, gentlemen, ladies, everybody has chosen a city. Perfect. And we're down to this one. Hopefully, most of you have done something with this. By the way, you can go to the Hellenic Statistics Association. Someone actually already did it. You can go there and you can actually figure out, they give freely statistics of per each island, I don't know, even per each city, of how buildings are distributed in terms of the age. So you can use that pretty nicely. And that's the easy stuff, okay? It will take you no time. Again, you can use Wikipedia, Google Maps to use this assessment. Again, I'm not asking you to do this for everything. I'm just asking you to do it for your island, okay? Or for your specific town that you choose. Now, here's where the interesting stuff comes in. You employ the area source model of share. And I have to explain a little bit. Remember logic trees? We've said a few things about that. There are multiple models and you can use multiple models. You can use discrete fault, smooth seismicity, area source. The easiest one to use is probably the area source. That's why we gave it to everybody. And why we don't give you all the faults and all the possible, models to run, because it's going to take a long time. This one will take, let's say, at most an hour run, most analysis. So we don't want to overburden your computer. So you're also going to use a single ground motion prediction. This is the NGA West 2, I believe, the Boer and Atkinson 2008. This is a simplified version, actually, of the NGA West. This is the simple one. That's funny because it fits in one paper. The other ones don't fit in one paper. They want multiple ones. They need multiple ones. You're going to assume 800 meters per second VS30. Remember, VS30 is the top 30 meters of soil shear wave speed. So for mountain areas, which I believe most of the small islands are mountain, so you need to use rock. Okay, again, this is not rock, it's just stiff soil. What really rock is, that's a long discussion, not for this course. But let's say this is like soft rock or very firm soil. VS30 of 800. Actually, it's borderline between A and B, right, if I remember well. And then you got your VS30 of 400, which is a bit of softer soil. Again, it's not soft soil in the same sense that Mexico City is soft. Let's say it's a firm soil, but of the softer variety, okay? For plains, we use this one. The larger islands are usually built not on a hill, but they're built close to the coast or a little bit of a valley. So best use this kind of number, okay? You can figure it out if you start seeing, if you see around, you look around, you see mostly olive trees and other stuff on a hill. Yeah, it's mostly mountain. If you start seeing things like Naxos like this, a lot of potato fields, you don't just see enough rock, it's mostly soil, and you know it's a 400 meters per second. Just look around your city. I mean, Google Maps can help you. Okay? Just to let you know also, there are apps with VS30 prediction based on the slope that you can estimate from satellite images. You can get the slope, and usually the shallower the slope is, the more likely it is that it's not a mountain. It's not it's more or less like a soft soil rather than a. So yeah, you can also use that. It's the Wild et al. It's available on the web. I can give it to you. It's no problem. But I think it's good to just go look at it and make a, let's say, an evaluation on your own. I want you to assess the seismic hazard for the entire Cyclades prefecture using a discretization of about 5 kilometers and produce the PGA hazard map. Probabilities of 50% in 50, 10 and 50, 2 in 50. This is classical PSHA again, and we want you to produce a hazard map for the entire Cyclades. It doesn't have to be huge, just pick a large area of the map that includes most of the islands and start running with that. This one is the only thing that is going to be about the same for almost all of you. Regardless of what island you chose or what town you chose, this one is the same because we're asking you to do it for all the islands. Okay, don't ask me if I include all the islands or if I've done it perfect. No, just get a big enough area that includes a lot of the Cycladic islands and you'll be fine. Okay? Now, if you choose exactly the same one as the guy next to you, okay, that would be weird, but no worries. Then I want you to compare your results to the Eurocode 8 Part 1 hazard map of your area. Actually, it's the same as the Greek hazard. I'm pretty sure I've given this to you. I'm pretty sure if you go to my courses, let's go to my courses, there you go. I'm pretty sure I have it here. Let me just, that's gonna be it. And it's in documents, I'm pretty sure. There you go. Quick semester project. I think I'm here. There it is. This is the design spectrum for Eurocode 8. And this is the hazard map for Greece, the design hazard. So you can see that most of the Cyclades, except this little part over here that includes Santorini, Amorgos, except this little part over here, this is the Cyclades, right? So except this little part over here, it's zone 1, 0.16 G. This part over here is zone 2, 0.24 G, right over here. Okay, so let's see, does your hazard map compare well to this one? I don't know, let's check it out. This, by the way, this one, what you see here is an older hazard map. It's the one you are producing, it's gonna be quite different because it's coming from a completely different model. Okay, so take a look at your My Courses. I mean, I can include this copy in your chat, but it's in your My Courses. What's chat? I should say everyone. There you go. So you can find this one over there. Oops. Oh, come on. What did I do with this? Yeah, that's the one I was. Oh, come on. There it is. Slow as this. So this pretty much takes care of question A. About question B. It's the settlement center, whatever we chose for you as the settlement. You need to estimate the seismic hazard curve for the 5% down spectral accelerations with periods of 0, 0.2, 5, and 1 second. As well as, by the way, 0 PGA, okay? As well as the uniform hazard spectra, the UHS, for exceedance probabilities of 50%, 10%, 2% in 50 years. Again, what should be the Eurocode elastic spectrum for your town and how does it compare to the official one? Meaning, again, over, well, come on. What have I done? I lost it. Okay, I'm an idiot. I go online. No, I'm not an idiot. I'm a supposedly smart person. Just not really. There you go. Yay. This is the Eurocode spectrum. You got it right here. Here's the formulation. AG, the design spectral acceleration, just needs to come from, sorry, this map. Let's try doing that with the AG, the 10 and 50 AG, of course, that you have calculated from your own analysis. Let's see, how does it compare? The shape is going to be like this, but it's going to be higher or lower, depending. And of course, remember, if you actually produce the 5% actual spectrum and not just the fitted of the Eurocode, you're going to get a very different shape in the end, because it's not going to go like that. It's going to be different. It's going to, for example, it's not going to be flat over here. There's no chance it's going to be flat. It's going to have a curve. It's going to change. And I don't know, is it going to fall like this with 1/t and then over here with 1/t square? I don't know. It will depend on your specific site and your specific results. Okay? So B is the part where you say, I think I know better than the code. Why don't I use the better information I got? A better job. By the way, again, it's often the case that you will indeed have better information at the site, and you will be able to do better design by simply saying, oh yeah, the code says 0.3 something. Actually, it's not this much, it's less, or it's higher. Why not use this data? Okay, for all of those, for all of you who did the course of steel structures, design of steel structures, right, in the previous semester, I actually had you do this, okay, based on the official Eurocode, not Eurocode date, ESHM 13. Side note, Eurocode 8 has not adopted the data and the seismic source model that I've given you. There is a new version of it that is coming out, ESHM, the European Seismic Hazard Model 2020, which is being evaluated, and it's probably going to be included as the Eurocode instead of this one. The problem with this one, to give you a bit of understanding, is that, well, if you go to Bulgaria, for example, and you start seeing what kind of values they estimated for their hazard, it's different from what Greece estimated. Why? Because everybody did their own little model, they excluded some sources, they used different assumptions, so it's not harmonized. You go like 1 meter to the north, 1 meter to the south, you get vastly different values. And this was a real problem between Italy and Switzerland, Switzerland and Germany, Italy and France. So everybody said, okay, guys, let's just do one model for everybody and make sure that we get consistency across borders and pretty much spots everywhere in Europe. So that one is going to be coming into effect probably, most probably it's going to be approved. Let's see. And it's going to come into effect and be part of Eurocode. Again, it's going to be what they call an informative annex. Informative means that you don't have to use it, but you should probably use it. So individual countries might come out and say, no, I don't want that one. I want my own. Maybe Greece will come out and say, no, I don't want to change from this one. So I don't know what's going to happen, but it's going to be part of Eurocode. Okay, and you have the chance, at least slightly order model, to actually do these comparisons. And that's important because this means that if you go today and you look at the structure and somebody has misjudged the hazard, and we misjudged the hazard, yeah, it has happened. And if I go back over here, you'll see that, okay, I should zoom a little bit. Athens is 50-50. Athens is 50% on zone 1 and 50% on zone 2. This happened in 2000 because there was an earthquake that actually pushed zone 2 much into Athens. Athens used to be just 0.16 G, and in 2000 we learned that, no, actually West Athens is not 0.16, it's 0.24. So yes, things change, codes get updated, hazard gets updated, and unfortunately a house that you built 20, 30 years ago now may not be up to code. Things happen. The question is, what do you do about that? Well, let's say for your island and for your case, what can happen. Now, point 4, it says find the MR scenario event with the highest contribution to the PGA hazard of the settlement at the exceedance probability of 10 and 50. And pretty much that's the aggregation we'll be talking about. You've seen it, how it's done. OpenQuake does it automatically for you. Just tell me what MR scenario event is the most important. That's all. So I think that pretty much covers. Yeah, there you go. We want a presentation of 8 minutes and 8 slides maximum, showing your results for items 1 to 4. So that pretty much covers it. Now, you ask me questions, as many as you wish, on this or anything we've said so far. And hopefully, okay, number one, you've done it. Number two, some of you have already done it. Within 2 weeks, you've done numbers 2, 3, and 4. Questions? Is everybody happy with this? We're good? We're relaxed?
I would like to ask something, but it is
Yes, please.
more general. Can we visualize the seismic source model, the area source model of the SER project?
Yes, you can actually see the sources. Yes, that's doable. On a GIS, yes. You can load it up on a GIS and you can see the area source model. Yes, that's correct.
Oh, okay, thank you.
I think actually I have it. You give me a second. I'm pretty sure I actually have a visualization like that for the source model. Let me show you. I'll actually, just a second, I'll get it. There it is. Here's an example. You can see here the area sources over the entire Greece. I mean, we're missing some here, but you can see, for example, the area source model that is covering, this is Andros, Tinos, and Mykonos over here. This is Syros. So you can see this part is one zone, and then this southwest part, which includes Milos, Naxos, I believe Paros is over here. This one is another zone. If you go to this part, that's on the southwest, is another area source. Santorini is on this part. I believe Olegandros, the other smaller islands, are on this part. That includes also the Dodecanese. So, yes. Multiple area sources. Actually, there are even some, I can actually show you. That's a very nice one that came out very recently. Which is, it was an interesting question. Actually, if you're interested, a pretty nice discussion of the, come on. Reports. Yeah, there you go. That's not mine, but a pretty nice discussion came out and contribution by, I believe, the University of Athens, National Observatory, ITSAC, other ones. It was regarding the Tyrnavos event. And you can see here, for example, there's the Aegean volcanic arc. Includes okay, the different areas. And okay, this is the lithospheric stuff, but I'm pretty sure they had somewhere with all the faults. No, that was the one. Okay, apologies. That was the one that was the yeah. So there are differences as you go from the North Aegean to the south. Okay? And that's actually a really nice report. I can send it to you if you will, if you wish. I think you can even find it online. Any other questions? Guys? Overall happy? Okay. The problem usually with online events and online lectures is that I know you have questions and I know there are things in your mind that are not perfectly clear. Because we're not in a classroom where I can see your face and I go like, see like those puzzle looks like, yeah, those wide open eyes or slightly sleepy guys as well. Yeah, it's tough to say, are you sure you got that, or to ask you specific things. So I'm hoping that they're gonna come out in the term project. Please start working on it, let's say, as of today, if you will. So the questions come up, you send them to us by email, and in the next class, in the next lecture, we're gonna be talking almost exclusively about the project. Angeliki is also gonna be helping us, showing us some a little bit examples here and there of things. because there are lots of things I'm sure you have not understood, have not tried, and unless you actually try them on OpenQuake, you're not sure about them, okay? So please do try to work this week through the project, come back, solve questions, and then we keep going forward, right? Phew. Otherwise, thank you very much. I think we're mostly done for today.
Thank you.
Thank you very much. Bye
Thank
bye.
you.
Thank you very much.
Thank you. Have a nice day.
Thank you very much.
Well, you too. Bye-bye. Have a great day, guys.
Thanks, Professor. Have a nice day. Bye bye.
Thank you.
Thank you.